On April 6, 1990, Chevron Perth experienced a lifeboat accident while conducting a boat drill at the Mina al-Bakar Iraq terminal. 2 persons were killed, 1 person seriously injured, and 5 other persons escaped with only minor injuries. The heroic efforts of persons on the scene were instrumental in limiting the loss of life.
It is with considerable sadness that I'm introducing this videotape concerning the tragic lifeboat accident aboard the Chevron Perth earlier this year. My profound sympathies go out to those who are injured and to the families of those who were killed. Because of Chevron's high safety standards and our high-quality operation, this accident has been a disappointment and a shock to all of us. It is particularly disturbing since it involves equipment and training procedures which are designed to prevent injuries and deaths. However, we can take some pride in the outstanding actions taken by those involved. There is the bravery of those in the lifeboat, the heroism of their fellow officers and crewmen in their attempts to rescue them, the rapid and professional response from the shoreside staff, and finally, the valuable assistance provided by non-Chevron personnel who were in the area at the time of the accident. This videotape presents an overview of the accident, the response to the accident, the ensuing investigations, the conclusions derived from those investigations, and the remedial actions to be taken to prevent a recurrence. The investigations were done not to find fault, but to determine the facts so that the cause of the accident could be identified and proper corrective steps taken at an early date. We strongly believe all those efforts are absolutely necessary to help you regain your confidence in the covered lifeboats and their launching systems.
My name's Dave Caldo, Assistant Fleet Manager with Chevron Shipping here in San Francisco, and I'd like to tell you about the events surrounding the accident to the Chevron Perth on April 6, 1990 in Mina al-Bakar terminal, Iraq. No cargo was ready for the ship after she had docked, so the captain decided to conduct his quarterly boats in the water exercise. Chief officer mustered the personnel necessary, the starboard boat was lowered and a drill was conducted and everything went well. The crew then went to the port boat, which is the enclosed Miranda lifeboat, and repeated the drill. The boat was lowered to the water, released, and the crew were exercised, and at this point everything was going fine. The boat returned to the cradle, was resecured with the launching pennants, and hoisting commenced. At about 6 feet above the waterline, the crew inspected the hook connections and to see that everything was okay before further hoisting took place. This was fine, and a signal given to the deck to resume hoisting. When the boat was about 35 feet above the water, just up level with the upper deck, some juddering took place on the boat, and at this time the after hook released. The boat immediately fell into the vertical position, couldn't be supported by the forward hook. Forward hook ripped out of the bottom of the boat, and the boat started to fall. It hit the water in an upside-down inverted position at about a 45-degree angle, immediately swamped through the open doors, and assumed a swamped, inverted position in the water with the 8 people inside. Meanwhile, on the ship, the chief officer immediately rushed to the starboard boat, mustered an emergency crew, released the boat in 5 minutes, and had arrived at the scene of the capsized boat. I can't begin to admire the professionalism that was carried out in this maneuver. To release that boat in 5 minutes and arrive at the capsized boat was an example of professionalism, good training, and extreme efficiency on the part of the boat crew. When the rescue boat arrived at the capsized boat, the chief officer and the first assistant jumped into the jellyfish-ridden water and immediately started their efforts to expedite the rescue of the 8 people contained in the lifeboat. Unfortunately, one of the persons who came out of the door suffered from water inhalation. The chief officer, recognizing this, immediately started to apply mouth-to-mouth resuscitation. Bear in mind that this is going on in jellyfish-ridden water, that in the end, the chief officer and the first assistant spent 2 hours in total in this water, a really heroic effort on their part. Unfortunately, the mouth-to-mouth resuscitation from the chief officer was not able to bring the Indian raiding back to life. As soon as time permitted, the captain sent the Purse Inch Rep report to San Francisco, and this triggered a number of actions on our part. The most important of which was to immediately issue a QNUT emergency message to the whole fleet, A, advising them of the incident, and B, putting a hold on all future drills until the facts were known. The next thing that San Francisco did was to provide help to the ship to assist the captain in dealing with the authorities in Iraq, and to provide help in obtaining further medical attention for the injured personnel. Captain Scala, our Marine representative in the Middle East, was visiting Egypt at the time, and he was immediately contacted and sent to Iraq. Our agency in Iraq, Gulf Agency Company, were advised, and they assisted in ensuring his access into Iraq in a timely manner. And he was able to reach the ship in short order and provide help to the captain, and was able to ensure that the radio operator, who by this time was in a hospital in Baghdad, was getting appropriate medical treatment. 3 extra superintendents were sent to the vessel to investigate the facts as quickly as possible. 2 came from Singapore, and 1 disembarked from a passing vessel. Captain Franco Segala rowed the ship from Dubai to Ras Tanura and back to Dubai to look into the operational aspects of the accident.
Well, of course, our first priority was to get the people and the ship taken care of, their needs, the injured and the replacement, so that the ship was able to operate with the full crew and with the replacement life rafts that were needed to be in class. After that was done, then we sat down to see, okay, where do we go from here with respect to knowing exactly what the problem was, what caused it, and where we should go to make sure it didn't happen again. We formed a committee in the office made up of representatives from our design and construction group, our maintenance and repair group, one of our superintendents, and one of our safety people. And their job was to come up with a recommendation and a thorough analysis of the accident. We quickly found that it was a very difficult job to know precisely what the cause of the accident was, but it was extremely important. We had to know exactly what caused this accident. And so we talked to some specialists from our engineering department, our corporate people, and they indicated that while they could probably do this work, they couldn't do it in a timely fashion, and we had to have a quick answer. They recommended a company called Failure Analysis Associates, which is an internationally known, widely respected, large company that does just this kind of work. They sat down and they came in with a specific proposal to do the in-depth technical analysis that we wanted to be sure we knew exactly what had happened in the accident. And we agreed with their proposal, we contracted for them, and we sent them right to work.
When failure analysis was first brought into this investigation, one of the first things we felt necessary to do was to go to Dubai and inspect the physical evidence that existed on the lifeboat that was involved in the accident. The main reason for this stemmed from the fact that this block, which held the Morse cable onto the hook, had perhaps failed and caused the accident. This block was found after the accident resting in the bottom of the lifeboat, separated from the hook. What we found in Dubai was that there was sufficient evidence to show that in fact this block was attached to the hook at the time when the boat hit the water. That evidence was contact marks between the block and this metal plate that is on the underside of the hull of the boat, thread impressions that were left inside the block when in fact this plate came down and sheared the block from the hook. Once we had determined that the failure of the block was not a primary cause of the accident, but in fact a secondary cause, this led us to refocus the whole investigation and to look for other causes that may have resulted in the hook opening up. In order to perform the various tests that we felt were necessary, we had to go inspect the accident-involved davit system on the Perth, and then we did some physical testing on the lifeboat system on the Burnaby. The purpose of going to the Perth was to determine exactly at what height the lifeboat was when the aft hook opened up and released the lifeboat. This I was able to accomplish by inspecting the davit, and I found that on the hoist ropes there were paint scrapings from where the wire rope in the falls had swung backwards and had scraped the adjacent handrails. This physical evidence allowed us to fix, with a great degree of certainty, the height at which the boat had been lifted at the time when the hook let go. After we had inspected the Perth, then we went over to the Burnaby, where we performed a load test while lifting a duplicate of the lifeboat involved in the accident. In fact, we did probably 20 tests where we raised the lifeboat up and simulated different raising and lowering conditions to try to quantify the maximum loads that in fact occurred or could occur while a lifeboat is being raised or lowered. One of those tests was in fact an actual simulation of the accident. Data from that test was used in our laboratory to simulate the actual loading condition on the hook during that process.
While failure analysis was investigating the cause of the accident, the ad hoc committee was busy determining the implications of this accident on the rest of the fleet. The flag states agreed to temporarily exempt the Chevron fleet from SOLAS lifeboat testing requirements. An emergency priority message advised the fleet to continue maintaining the boats, but that no one was to enter the boats unless the hanging-off pendants were installed, or in case of an actual emergency. Also, the committee synthesized the results of lifeboat inspections conducted on the rest of the fleet. These reports revealed a variety in the types of lifeboat releasing gear installed and variations in maintenance practices. Ulf Dahlgren, chairman of the committee, explains.
Well, we found the level of maintenance to vary greatly among the ships. Some were in excellent condition. Others where we found the clamps were rusty, the cables needed lubrication, and in some cases we found the release hook having been painted. Originally, these release hooks were made of galvanized steel and should not need any kind of a coating, only lubrication. Well, as we continued to probe further, we found a number of variations among the boats. For example, on 4 boats, we found the hydrostatic release was not fitted. On one ship, we found the hanging-off pendants missing. Various types of cable had been installed. However, I don't consider that to be of a very serious nature in that manufacturers of these Morse-type cables make them to equivalent standards. They also found some of the bolts for the clamp lock to be of various materials. We find these great variations in maintenance among all of these boats, yet all of the ships are using the same maintenance checklist, be it from the manufacturer or from Chevron. We determined that there are about 4 different kinds of releasing gear on our ships in the fleet.
The most common lifeboat in the fleet is a watercraft boat fitted with Titan release gear. It is this kind of boat that was involved in the accident. U.S. flag vessels use Viking release gear. The R. Hal Dean and the John Young also have different systems. All these systems meet SOLAS requirements. Failure analysis was convinced that the accident was caused by a failure in the Titan release system. The releasing mechanism, including the aft section of the lifeboat, was shipped from Dubai to Menlo Park, California, for extensive testing.
Failure Analysis Associates did a number of things to do a comprehensive investigation of the Chevron Perth lifeboat incident. Among those things that we did was a mechanical test in our mechanical testing laboratory at Failure Analysis Associates in Menlo Park, California. To do those tests, we used actual gear from the lifeboat itself, the one involved in the accident. You've probably noticed that the hook in our test apparatus here is actually upside down. The reason for that is for safety purposes and for easy access for us to do this testing. If the hook were right side up, it would actually be at the top of this test machine and difficult for us to access in these tests. The fact that it is upside down has no effect on our test results. You'll notice that the hook is now in the release position. It could not be used to lift a lifeboat. To get it in a position to lift a lifeboat, you must cock the hook, and I'll now show you how that's done. There's a lever on the side of the gear that's used to cock the hook. If I put the hook in a position where it could be used to lift a lifeboat through a ring like this attached to a cable, and then I move this lever to a cocked position, then the hook is locked in position, and it's in a position, a locked position, so that it can lift the lifeboat. Now I would like to show you what happens on the other side of this gear when I pull this lever on this side that cocks the hook. So let's turn the mechanism around this way so that you can see the lever on this side of the gear. You'll notice that this lever is attached to the Morse cable, which in turn is attached to the control box. So when I pull the gear that cocks the hook, you notice what happens to this lever. So I'll now pull this gear that cocks the hook. You'll see that this lever has moved the Morse cable, which then controls certain mechanisms in the control box through this Morse cable. Before cocking the hook, the crew should set this handle in the control box so that it is just above these slots in the side of the control box. At this time, the handle tangs are riding on top of quadrants inside the control box. Now, if you'll notice, this quadrant will move when the lever is operated back at the hook. Now, as you can see, that quadrant moved, and the tangs on this handle, by the spring action inside the handle, moved to the bottom of these slots. Now the handle is in a position such that this safety pin can be inserted. Once this gear is in this position, with this handle in this position and the tangs in the bottom of the slot, that means that the hook is properly cocked. And this gear can lift the full weight of a lifeboat and even much more.
After comprehensive testing in the laboratory and extensive interviews with the officers who were on board the lifeboat at the time of the accident, failure analysis determined the sequence of events that caused the hook to release.
Based on our entire investigation, including the testing that we've described for you here, I would now like to tell you how this accident happened. The lifeboat with the crew inside was lowered to the water. Then the crew released the lifeboat by first pulling this pin and then pulling this lever back to this position. Pulling this handle back opens the cam, which releases the hook and frees the lifeboat from the ship. After that, the crew made some maneuvers in the boat and came back to the ship to hook up. To accomplish this, the aft hook is rotated back into position to be cocked. The lever that cocks the aft hook was rotated into this position, where some resistance was met. Similarly, the forward hook was cocked. You will notice that for the aft hook, the lever was not rotated all the way against the stop. What this implies is that for the aft hook, the hook was not completely cocked. That is, the cam inside was not rotated completely to a position where it's flat against the edge of the hook, so the hook is not completely cocked. Notice that the handle is now in a position where the tangs on the handle are riding on the rim of the control box. The handle was then moved to a position over the slots and dropped down into the slots. But you notice that the tangs are not all the way down into the slots. Next, the safety pin was inserted. Notice that the safety pin goes in despite the fact that the tangs on the handle are not all the way down into the slots. The reason that the tangs are not at the bottom of the slot is because the hook is not completely cocked. The next thing that was done after the pin was put in place is that the hooks were checked by shaking and rattling to see that they were set. Despite the fact that they're not completely set, they appear to be when you attempt to shake them. The boat was then raised to 1 meter, and it was stopped, and then the hooks were checked again. Again, they appeared to be secure. The lifting of the lifeboat continued, and the dynamic action of the loading from lifting the lifeboat eventually rotated the cam, which was not locked into position. The hook released, and the lifeboat fell. We've described for you the sequence of events that led to this accident. Now we'll talk about some things that could have been done to prevent the accident. The first of these is that the manual prescribes that this handle will be moved to the position over the slots before the hook is cocked. If you recall, in the accident sequence, the hook was cocked first before anything was done to the handle. Now you notice that with the handle in this position, that will be very easy to cock the hook. I have the hook in place, I pull the lever, and it goes very easily against the stops. It does not meet this resistance that it met when the handle was in the improper position. Now that I've cocked the hook, I go back to this position at the control box, and you will see that the tangs of the handle are down in the slots where they belong. So the system is now completely locked up. The hook could not be released, and this accident could not have happened if the handle had been moved over the slots before the hook was cocked. Another way this accident could have been prevented was if this modified handle had been installed during a retrofit of this control box. At the time of that retrofit, this hole that the pin is in now was drilled through the housing. It was intended that this handle, or a handle like this, would have been installed so that when the pin was passed through this hole and the hole on the other side, it would also pass through this hole on this tang on the handle. If this handle had been in place, the crew would not have been able to insert this pin through these holes unless the tangs on the handle were dropped down to the bottom of these slots. This would have alerted the crew that the handle was not in the proper position, and hence the hook was not in the proper position, and therefore was not locked.
We're very satisfied with the work that FAA has done in this investigation. We expected a lot from them, and we knew it was a difficult task. But having reviewed their final presentation to us, I'm very impressed with the exhaustive, complex, and very, very thorough investigation on site in Dubai, using actual models of the boat in Southampton, and then bringing a part of the boat to recreate it in their laboratory in Menlo Park. They left nothing unturned in their search for finding the cause, and including interviewing our people and looking not at just the physical element, but the human element of their study. I'm confident that the Watercraft Titan system is a safe system to use on our lifeboats if the hooks are properly set with the cam in the right position relative to the safety hook. The hooks operate in conjunction with a bigger system of cables and levers, and because of modifications and differences in the designs, we have to be very careful about the operation, the proper operation of the entire system. Early in the investigation of the Chevron Perth accident, we surveyed all the vessels of the fleet, and we learned that some of the other boats, watercraft boats, had experienced similar failures of the release gear. Whether with the gear let go with the boat in the stowed position or whether it was very close to the water, there were no consequences to speak, that is personal injuries, and perhaps this was taken for granted. In hindsight, we think that any failure of any mechanical equipment where there could be consequences to ship safety or personnel safety has to be reported to the Home Office to be able to enable us to have the chance to understand whether there is a trend, a safety design problem, but at least to allow the ability to provide an analysis investigation to assure the right margin of safety for all of our critical equipment. I have a feeling, as a result of the analysis and the investigation of the accident that we've just concluded, that there was a false sense of security regarding the watercraft lifeboats at a number of levels. In the Home Office, for those of us that were involved in the purchase of the lifeboats, to the fleet people who maintain them, but more importantly to the operators of the boat on the Chevron Perth on that day, where they felt that the boat hooks were properly set because the handle was in position with the pin secure. The fact was that because of the arrangements and the modifications of that release handle, the pin did not give them the security that they needed. We have to constantly remind ourselves that where we are in operating situations where lives or injuries are at risk, that we have to double check and triple check all possible circumstances that could be the difference between safety or accident.
After we were sure that we knew the cause of the accident, we then wanted to be sure that we got the information out to the fleet just as soon as possible. And that's the purpose of this video, so that everyone in the fleet knows exactly what happened and what we're going to do in the future to make sure that we don't have this kind of an accident again. In addition to the video, we want to send a superintendent out to each vessel to talk in person about the causes, what we need to do about our training to make sure that we do lifeboat drills properly in the future, and to make sure that we keep up the maintenance and protection of the lifeboat systems that we have on board. We want to resume our lifeboat drills just as soon as we can, and we're going to do this by using a new device called a safety strop. And this was a device that was first suggested by Captain John Betts. It's a cable a little longer than the regular cable that runs to the hooks on the lifeboat, and it will be used only during the lifeboat drills. By attaching this safety strop, it will make sure that we cannot drop the lifeboat in the event that a hook releases. And we have to be sure, however, that this strop is only on the boat when we are doing a drill. And we will make sure that we have placards in the boat so that after the drill, the safety strop is removed, and therefore the lifeboat is ready in the case of a real emergency. One thing we learned from our investigation of the accident is that we need a better lifeboat training program among our fleet officers and crew. We plan to develop a new program, a new video that replaces all of the old slides and film that we had. And this new program will be shown to everybody in the fleet, and there will be a certification program as a part of this so that everybody will be certified and tracked that they have been certified on the lifeboat training program that we developed. Another thing we found is that we need more clearly understood and easier to read instructions for the maintenance of our lifeboat systems. Well, the information is there, it's not always clear, and there are differences from one ship to another as to exactly what the maintenance practices should be. We plan to standardize our instructions so that everybody will be following the same clear and proper maintenance instructions for all of our lifeboat systems. We're also then going to go on and look more in depth at what type of system we should have for hoisting the lifeboats. It could be that we will want to modify some of the systems that we have currently. At this point, we don't know whether that's required or not, but we plan to continue with our investigation to make sure that wherever we end up, we will have the safest, best system out there that we possibly can have. That's our objective.
After viewing this program, I sincerely hope that you can agree with me that Chevron Shipping Company has taken the steps necessary to determine the true cause of this accident. We are convinced that we know the cause of the accident and are confident that the interim countermeasures recommended will prevent a recurrence. The covered lifeboats and their launching systems are an integral part of our safety system aboard ships, and it is necessary that we restore our confidence in using them to protect lives. I want to thank all those people that were involved, because with their frank and honest assistance, we were able to carry out a thorough investigation. If you have any comments, suggestions, or questions concerning what you have seen in this program, please do not hesitate to communicate them to Fleet Management, because we all have the common goal to keep Chevron Shipping Company the safest in the business, and this can only be done with your valuable assistance.